Okay, now let's continue by the second subtopic, which is 7.2. The topic is gravitational potential energy. So based on this subtopic, for the learning outcomes, students should be able to define and use gravitational potential energy. So what is the gravitational potential energy and how do we use the equation in calculating something lah. Alright, so let's start by the meaning of gravitational potential energy. So gravitational potential energy, the symbol is capital U, is defined as the work done by the gravitational force to bring a test mass from infinity to a point. Okay, so this is the mass. So the work done by our gravitational force in bringing this particle from infinity to a point which is nearer to the planet lah. Alright, so work done here now representing the gravitational potential energy. So in this case, we are bringing this particle from infinity to a point where the distance between this point and the center of the planet now is R. Okay, so the potential energy at A now equals to Gmm over R and negative. Alright, so this is the potential energy at point A, which is equals to the work done in bringing the mass from infinity to be here. That is our gravitational potential energy. Okay, how do we get this equation? Alright, so let me show you the derivation. As long there is it's not in our syllabus, but let me show you how do we get this equation. Alright, so according to the equation before, Fg, the gravitational force equals to Gmm over R squared. Alright, as we know, work equals to, before this, Fs. But in this case, the replacement now is R. Okay, we are discussing about the motion of the object. Okay, measured in R. So now work equals to the integration of F with respect to R. Okay, so what F is that? Fg lah. We are discussing about the gravitational force. Okay, between R initial and R final, starting from infinity to a point where the distance is R. So R1 is R initial, R2 is R final. Okay, we just substitute Fg to be here. And then you will get work equal to the integration of Gmm over R squared with respect to R. Okay, from R1 to R2. Alright, so R to the power R to the power of 2 still equals to R to the power of negative 2. We just bring R squared to be here. From bottom to be at the upper side here. You will get R negative 2 lah. And then Gmm just a constant, isn't it? Alright, so we don't have to integrate these three things. Okay, we just integrate R to the power of negative 2 with respect to R. So that you will get Gmm R to the power of negative 1. Mathematically, you will get this. So, something is missing here. Starting from infinity to the final position where the distance is R. Okay, alright. So, based on that, R to the power of negative 1, okay, we just transfer R to the bottom again, and then you will get this Gmm over R. Still the same, no more negative. Okay, and then Gmm just a constant. You just take out Gmm to be outside here, and then what do we have now? 1 over R, starting from infinity to a point at R. So 1 over R giving you 1 over R lah. This is final. Minus initial 1 over infinity. So 1 over infinity giving you 0. So at last, you will get the equation to be like this. So work equals to negative Gmm over R, which is equals to our potential energy, and we call it as gravitational potential energy, which is equals to the work done in bringing any particle from infinity to a point at a distance r from the center of the planet. Okay, and one more thing, don't forget that the unit of energy here should be in joule. So again, U is our gravitational potential energy, and the unit is joule, or the symbol is capital J. Alright, okay, so what does mean by negative here, and what is m, small m, r? Alright, so let's continue by this. Okay, let's say we are discussing about our planet, which is Earth. Alright, so U equals to negative gm of Earth, m of the object, which is bringing from infinity to a point, okay, and then r should be radius of the planet, which is Earth. Alright, so the gravitational potential energy of a body of mass m at the surface of the Earth just be like this. Okay, so again, this is mass of the object, which is moving from infinity to a point, and this is the mass of the planet, which is Earth, also r of Earth. Alright, so what does it mean by the negative sign here? The minus sign indicates that the gravitational potential energy at the surface of the Earth is less than at infinity. Okay, it follows that a body at infinity will fall towards the Earth. A body on the Earth does not fall to infinity. Okay, anything just falling down, isn't it? It's just moving towards the planet. Okay, that is why we got negative sign here. Okay, so this is the gravitational potential energy, where the symbol is U. Okay, how about the change in gravitational potential energy? Alright, what do we have? Okay, so the change in gravitational potential energy, which is delta U, is given by, of course, delta U equals to U final minus U initial. Okay, for example, now the object is moving from point 1 to point 2. So this is initial position, and this is the final position. The initial position is located at R1 from the center of the planet, and the second position now is located at R2 from the center of the planet. Okay, so the object is moving from 1 to point 2. So delta U should be U final minus U initial. The final position is point 2. The initial one is point 1. So delta U equals to U2 minus U1. So U is gmm over R, so that U2 is gmm over R2, remember negative, and the energy always negative here, minus U1. U1 is gmm over R1, and negative again. So negative and negative here become positive, so that by rearrange the equations, you will get something like this. Okay, you will get gmm just a constant, just take out gmm here, and then 1 over R1 positive and minus 1 over R2, you will get this. Alright, so mathematically you will get this. Alright, and then okay, you will get this. Okay, how do you get this? Okay, by assuming that R1 and R2 is quite near to the Earth's surface. Okay, seems like R1 equals to R, capital R. R2 also equals to capital R, where capital R now representing the radius of the planet lah. So here R times R giving you R squared. Okay, so if the test mass M stay close to the Earth, then the denominator we may replace R1 and R2 by R, because they just multiply here. So giving you greater values, so we take it as R squared, and again gm over R squared, so gm over R squared giving you gravitational acceleration, isn't it? Alright, so you will get this lah. I think something is missing here, and gm over R squared, something is missing, m. Okay, m is missing here, we got another m here, m, and then R2 minus R1. So gm over R squared now giving you g, and the gravitational acceleration multiplied by m, and then multiplied by R2 minus R1. Okay, so R2 minus R1, so this is R2 minus R1, giving you the difference now between these two positions, which is H actually, and the height of the object, which is moving from initial to the final position. So that R2 minus R1 equals to H, giving you delta U equals to mgh. All right. So this is the change in gravitational potential energy, and this is the way how do we get the equation. There is no derivation in our syllabus, but I want to show you how do we get this. Okay.